And now the end is near, and so I face the final curtain. My friend, I'll say it clear, I'll state my case, of which I'm certain. I've taught a class that's full of theory gems and its foundations and more, much more than this. I did it my way. Yes, I did do it my way, but credit where credit is due. In preparing this class, I used a lot of materials from previous teachers of CS154 at Stanford, and mostly Luca Trevisan and Ryan Williams. So thank you, Luca, Ryan, and other teachers. And this is the last video of this course. And I want to tie some of the ideas back. Um, so some parting thoughts when we are going to part. So first, let's kind of look back at what we've done. We had 3 chapters. In the first chapter was about finite automata, where we discussed a very simple model of constant memory, and we characterized what can be computed through closure properties. We saw this notion of regular expressions, which exactly capture regular languages. We encountered non-determinism for the first time, the power of verified guessing, and we were able to argue and characterize what cannot be computed through the pumping lemma and through Mile-Narrow theorem. And we also discussed optimization, finding the minimal DFA, and learning, which was more complicated. We also discussed a more modern version of DFA, which is streaming algorithms, and we discussed the complexity theoretic notion of communication complexity that was very relevant. We saw how to use what we learned about DFA to deduce things about streaming algorithms, and we were also able to take ideas from communication complexity and results from communication complexity to learn back on streaming algorithms and DFAs. In the second chapter, we talked about computability theory. We introduced a very powerful model, Turing machines, and even beyond, we talked about later Oracle Turing machines with oracles that are very powerful. We discussed what cannot be decided, cannot be computed at all. Our foot in the door was ATM, which was undecidable, and not ATM, which was unrecognizable. This was after we also showed using counting that unrecognizable languages exist. And then we talked about mapping reductions, and we've seen many more problems, most of them about computation. And we discussed kind of a hierarchy of exceedingly harder problems through this notion of Oracle machines. So we talked about halt and super halt and super one halt, etc. We then discussed the foundations of mathematics and computation, the Gödel theorems, and we shown that there are limitations to the ability of basing all of mathematics on a very powerful system, mathematical system, logical system that can then be automated. We talked about Kolmogorov complexity, which was a universal theory of information through this notion of Turing machines, and we tied everything together. In the last chapter, we talked about complexity theory, which is a very active area of research today and for many decades now, with a lot of impact on many areas, such as cryptography, but other areas as well. We talked about time complexity, we talked about P versus NP, NP completeness. Uh, so this was where non-deterministic came back, and it was very powerful here. Our foot in the door here was SAT, a problem that is NP complete, the first problem that we've seen that is NP complete. And then again, through reductions, but now polynomial time reductions, we've seen many more problems, and there are many, many more problems. And on the technical level, reductions are something that is very useful, and this class tried to discuss. Again, we saw a hierarchy of hard problems that became harder and harder. And this is the polynomial hierarchy. We had NP and NP to the NP and NP to the NP to the NP and so on. And we also discussed mostly space, and we related space to time. We saw the impact of non-determinism in space. We also mentioned randomness in one of our videos, but in much less detail and as an advanced topic. We also discussed algorithmic fairness and showed that the impact of this theory modeling can be very, very real. And today in this video, we're going to discuss a little bit more about crypto. We already discussed a little bit about crypto when we discussed randomness, game theory, and talk a little bit more about the computational lens. But again, much of what we've seen about randomness, about algorithmic fairness, and other topics already encapsulating within it notions from the computational lens. So kind of going back to what we discussed at the beginning, computing is the evolution of an environment via repeated applications of simple local rules. That's a definition due to Avi Vigderson, roughly. And this allowed us to look at many, many phenomena as computations. Things like protein folding that we mentioned, or the way the brain computes, evolution, quantum processes, and also social processes like the 6 degrees of separations that we mentioned, and the markets, economic markets that we will discuss a little bit more. So I've seen that recording a video doesn't work well, so I'll refer you again to the webpage of the class, and where I'll put a link to the Hitchhiker's Guide to the Galaxy. This is kind of a proof for the power of the computational lens, and it discusses, this part of the video discusses a very powerful biologic computer, and that we are all familiar and very reliant on. It's a physical and biological computer, very important to all of us, and you will need to see it by yourself. So let me give you one more example through this computational game theory. So in game theory, often we have these solution concepts that try to predict the behavior of some interaction. When we assume that the parties are rational, they're trying to maximize some utility. For example, in a market, and a notion that one notion of equilibrium, it's actually not one, there are several variants of this notion, is an equilibrium, such as Nash equilibrium. And the point that the computational perspective shows is that yes, perhaps an equilibrium is something that if you are at the equilibrium, perhaps you will not move from the equilibrium. So then it would predict your behavior if you're rational. But how would the market find this equilibrium? This must be part of the equation because if computationally it's impossible to find an equilibrium, then the market will not find this equilibrium, and therefore it would not predict the behavior of the market. So there are lots of work about simple dynamics that reaches equilibrium. So this would also perhaps suggest which equilibrium, perhaps there is more than one equilibrium, which equilibrium the market will discover. One, kind of to give you an example of a simple dynamic, one of it is best response. So you have many parties, and at every given point, parties change what they're doing to be the best thing that they could do now, given what everybody else have done. But now that one party changed what they are doing, some other party may also want to change because now what they're doing is not the best. And sometimes this dynamic of best response converges into some equilibrium. So this could be an instance where there is not only an equilibrium, but there is a simple way to reach this equilibrium. Another notion, and that really preceded the computer scientists kind of getting into game theory, is but computer science, I think, have strengthened our understanding of this notion, is the notion of bounded rationality. Um, so, so perhaps parties are trying to maximize their utility, but they may not be able to maximize their utility because it may be computationally hard, and therefore modeling parties that are not computationally unbounded but rather bounded, therefore their rationality is also bounded, can be useful. So an example, a famous example, is that of the prisoner's dilemma, which I'm sure many of you heard. So there are two prisoners. They're caught for some offense. Perhaps they were caught with illegal weapon, but they're suspected to have planned a much more serious offense. And therefore, the police is trying to talk with each one of them separately, try to convince them uh, to admit to the police the real crime, and then they will get off more easily. So this is kind of their utility. If both of them cooperate, and here cooperate is with each other, one prison with the other prison, then they will only get a punishment for the weaker offense that can be proven, for example, carrying a weapon, an illegal weapon. If one of them uh, uh, tells on the other, then B, this one that tells, will get off. So instead of 2 years, it will get 0 years, and the other one will get much more, 10 years. And similarly, the other direction, if both of them will actually admit for this crime, then there is no point in giving them a discount, and therefore both of them will get 5 years. The point that has been observed in this situation, that although the best thing for them to do if they can coordinate is both of them cooperate with each other, this is not an equilibrium. So no matter what prisoner B does, prisoner A has an incentive to work with the police, because if prisoner B cooperates, then instead of serving 2 years in prison, A can get out immediately. And if prisoner B already tells on prisoner A, then A might as well also tell on B, and then reduce its own sentence from 10 to 5 years. But the point that was observed is that that doesn't capture actual behavior. Often they will stick to their guns and not admit to the bigger crime. So what's missing here? And there was an entire beautiful literature in game theory about it. For example, the notion of repeated games. So the idea is that yes, if you do it once, then perhaps it's better to always tell on your partner. But this is a repeated game. Perhaps you will have future interactions, and it's better for you uh, to cooperate with the other prisoner, and then it will help you in the future. Turns out that if you do it for a finite number of times and both parties know how many times it is, then this doesn't work. Because once it's the last time, then A and B have an incentive to tell on their partners to defect from each other, and therefore the last the one before last time, they also have an incentive to defect because they know that it will not affect them the next time. Anyway, the next time both of them are going to defect. And this is what's known as backward induction. Will show that they will defect all the time, meaning that instead of serving 2 years every time, they will always serve 5 years. Um, this changes if it's finite, or perhaps if it is if it if it's infinite, or perhaps if it's finite but you don't know exactly when it's going to end. And one way of getting it is through modeling each one of the parties as a limited computation, specifically as a finite automata. That's a result due to women who got the Nobel Prize for economics. And if both parties are a finite automata, then we know that they cannot count. So they cannot know when does the sequence end, and therefore they will. It turns out that now they do have an incentive to cooperate. Of course, modeling parties through a finite automata perhaps is not the most realistic way of modeling bounded rationality, and I think that the theory perspective has brought more sophistication to this idea of bounded rationality. And once you want to cooperate, there will be various different efficient um, um, strategies, which I will not discuss here. I want to say that the computational lens have given new interpretation to topics um, that we care about, and I gave you already many of these examples in this class. The notion of proof changes dramatically when we think about parties as being bounded, when we add probabilistic proofs and interaction. The notion of knowledge changes when you think about things that are computational. So you have zero knowledge proofs. These proofs, and you have encryptions. These are things that in them there is more information. There is much more information. Like in the zero knowledge proofs, there is enough information. For example, if we want to a zero knowledge proof that some graph is three colorable would likely give all the information about the coloring if the observer is computationally unbounded. But if it is bounded, then they cannot access this information. So the information is there, but it doesn't translate to knowledge, because for knowledge you need to take into account the computational power. Learning we discussed as a computational tasks. Randomness and entropy through this notion of pseudo-randomness changes dramatically. So all of these notions and others that are very basic change when you take computational resources into account. I want to also say that this idea of computational hardness, which we don't necessarily like, we want to be able to solve everything, does have some positive impact to it. And in any case, it has a lot of impact. So remember or recall this notion of factoring, and if you assume that factoring is hard, meaning that given two primes that are large and p and q, and you look at their product n, which is p times q, and p and q are chosen in some way. If you assume that you cannot factor it, you cannot derive p and q, then this gives you what's known as a one-way function. There are many ways of getting one-way functions based on various assumptions, various computational assumptions. But if you assume this hardness, if you assume that you cannot factor, or if you assume that you have this more abstract notion of one-way functions, then you get lots of interesting stuff. You get random instances of SAT that are hard. We mentioned that SAT is hard in the worst case, but perhaps in practice, usually SAT solvers would solve their instances. But using cryptography, you can create instances of SAT or a distribution of instances of SAT that you cannot solve. You have this notion of zero knowledge proofs once you have these one-way functions. Uh, you have hardness of learning. You have very simple classes of functions that you want to be able to learn, but you cannot if you assume that factoring is hard. You have pseudorandom generators. So you have a way to create more uh, or something that's effectively random out of fewer truly random bits. So you create lots of pseudo-randomness from a little bit of true randomness, which this means that randomness is weak. And in general, you have cryptography if you assume this kind of hardness, one-way functions, or sometimes you need to assume even more. So I want to kind of, towards the end, also re-mention this picture again by Avi Vigderson that really shows how powerful the theory of computing is. And we have been dealing mostly with the core of TOC, the core of the theory of computing. But once you have that, it interacts with many other areas within theory, like algorithmic game theory, logic, randomness, learning, property testing, verification, distributed computing, communication complexity, quantum computing, cryptography, and all of those interact with many areas outside of theory. Computer science more generally, mathematics, statistics, social sciences, biology, physics, economics, and in all of them, theory have been able to make important contributions. So even, for example, in mathematics, we usually think about mathematics as an area from which we gain tools for our theory analysis, which is absolutely correct. Theory has been able to develop tools that help solve problems that mathematicians have cared about. This is indeed a beautiful picture. And with that, I'll give the final parting thoughts. Computation is a powerful notion, and it's becoming increasingly central to our understanding of the world. Theory allows us to model and analyze computation and reaching non-trivial understanding. And I hope that you appreciate that even within this course that is still very basic, you manage to see very non-trivial things. Even things like mile-narrowed or pumping lemma, or the fact that ATM is undecidable, or the fact that 3-sat is NP complete. All of these are very non-trivial understanding of computation that you can now understand and have in your fingertips. There is much that is still open. We're waiting for you. And with that, I will conclude this course and conclude this video and this sequence of videos. And I want to thank you for taking part of this course. It is very strange to have a sequence of videos. I much more enjoy being in the class and having it interactively. I do get a little bit of that through other meetings that we have, but I hope that these videos by themselves are useful for you, and I thank you for your participation.